Okay, so last time we talked about normal faults, reverse faults, and strike slip faults. So to start off today, this section here, we're going to talk about how we can identify these a little easier. Okay, and so first thing we need to do is to give you some of the clues on how to do this. And it's nice and dandy to see a block like this, a block diagram like this, to be able to figure it out. But what about in an actual picture or out in the field? How would you identify that way? So I'm going to show you some examples here. Now in this picture, it's very easy. What you see here is what we call marker beds. Now these marker beds have changed. So for example, this kind of grayish one in the middle here, notice that it's gone down relative to the other one here. So we know that this is the hanging wall block. Okay, this is the footwall block based off of its relationship to us. And then we know the hanging blocks move down relative to the football wall block. Therefore, that is a normal fault, right? Because you can see that the marker bed has moved down relative to each other. So that would be a normal. Now, if this moved up relative to this, we'd call that reverse. So a lot of times we look for what we call marker beds. Okay, and you can see that, I think, in the diagram here, where you see the marker bed here, we can see the difference as it goes down. Here's the marker bed on this one, where it's moved up here it's been cut off here and moved up, and that you can say that this side, which is the hanging wall, has moved up relative to the foot wall. That's a reverse. Okay. Now there is a difference between what we call a reverse and a thrust fault. This is something that's talked about in your text. I don't talk about it a lot in class. I just know that reverse and thrust are pretty much the same type of fault, except thrust is a low angle one and the reverse is a higher angle one. That's the only difference. And so I use reverse and thrust pretty interchangeably for our class. Now, if I was doing this in a more advanced class, I would distinguish between the two. But for us and our purposes, they're pretty much identical. Okay. So other ways we can actually figure out if there's a fault are some features that we might want to go along with it. One is what we call a fault scarp. Now, if this fault actually ruptures the surface of the ground, okay, and this block were to move down, there would be this extra space right up here that would be now exposed. It's the fault surface that is now exposed on the surface of the ground. We call that the fault scarp. That's the surface of the fault plane that is now exposed. Okay, so in this one here, this normal fault has displaced the ground surface. The exposed step is what we call the fault scarp, right up there. Okay, now when those rocks slide past one, there's lots of pressure on these rocks, and so it will actually shine up and kind of like form grooves on the surface of the plane sometimes. And we call these slicken sides, which are just polished fault surfaces, and then the slip lineations are the grooves that you can find in those polished areas. So here's the polished surface with a striation orientation this way, which means the fault was moving back and forth in this direction. Those are the things that we can use to identify faults. Now in your pictures, you're going to be using what we call the marker bed technique, okay, that we use in the class, because you're not out in the field looking at and touching these rocks, but those are ways you can do that if you're out in the field. Now, so we're going to do a little bit of tests, and I know in class I would actually poll the class and we'll see if everybody's getting this idea. I can't do that on an online section. However, I'm going to still hopefully just do it with me as you go. Okay, so what kind of fault is this? First thing that you should do in this is find a marker bed. And in this one, you can see nice, distinct marker beds. There's this one right here and this one right here, which were once attached. If you look at these other ones, you can see up here, there's like this 1, 2, 3, 4 kind of beds together. And there's a thicker difference, and then there's another one here. You can see the same thing here, 1, 2, 3, 4, and a thicker bed, and then up there. So you can see that they matched up across. These all could be distinct marker beds, but this is probably the best one here. So this is the fault plane right there. And then this side here would be the fault, the hanging wall or the foot wall. In this case, it's the hanging wall, because remember, this is on top of the fault surface. Okay, so if I was standing here, my hands would be up at the top, and that would be hanging from the top. So this is the hanging wall, this is the foot wall. So in this case, the hanging wall is moved up relative to the foot wall. So we call this a reverse fault. Okay, so this is supposed to be a joke, by the way. If is this a normal fault, a reverse thrust fault, strike slip fault, or not my fault, right? It's corny, I know, but my students in class sometimes chuckle at it. Okay. Anyways, the point comes is that this is a reverse fault. Okay, as it moves up, it would be a thrust if it was lower angle. But this one right here is reverse. Okay, so there's the marker beds that I'll show you. Okay, what kind of motion? Oh no, let me draw in the fault plane. So there's the fault plane right there. Okay, it's off a little bit in some places, but you can see the point. Okay, what kind of motion is this? How do I get this block to go over top of the other block? Well, I have to push, right? So if I have my block systems here, to get that same kind of material where the hanging wall goes up over the other ones, I have to push on it. Okay, to get that push on it, that means that I have compressional force. So I have compressional motion here. Okay, so this is a reverse fault with compressional motion. Now, what kind of plate boundary? If this was a plate boundary, it's not. But if it was, what kind of plate boundary would this be related to? And of course, hopefully you know that if it's coming together, this is a convergent plate boundary, right? Okay, that makes sense to you? Now, this one, we're not looking at the rock on its side now. We're looking from down above. Okay, so this would be an example of what we call a map view, looking down on it. And this first of all, let's find the actual fault plane. Fault plane's right through here. Now you can't tell if this is what we call a dip slip fault, where it's going up or down from here, but you do notice from the marker beds, let's say these two marked up, that you actually had these separated. So this one actually here is shearing past one another, and we call it a strike slip fault. Now, is this a right lateral strike slip fault or a left lateral strike slip fault? Well, if this guy here, let's call this number 1, okay, and this was number 1 too, that means this block over here had moved to the right, so we'd call that a right lateral fault. Okay, but let's say that this, I'm going to do a cross now here, is that one. Okay, that means this this has moved to the left, so that means that's a left lateral fault, if that's the case. If this lined up to that line, it's a left lateral, but if this one went up to this one, it would be a right lateral. Now, on this one, I know it's a right lateral because this is the San Andreas fault, and the San Andreas fault is a right lateral. And so I know that that one is, I think, yeah. Okay, so I think if I remember right, this is the one that's actually attached to this. So it is a right lateral fault. Okay, what kind of motion would this be? Now we know compression would be going to make it smaller and have the hanging wall go up to the foot wall, whereas extensional means it's going to go the opposite direction. So this is shear. Okay, and if it was a plate boundary, this would be a transform boundary, right? Okay. Last one. Now here I put the marker beds here. This one's a little harder to figure out where the marker beds are, so I gave the lines to you. So I have one there, one there. So that means the actual fault plane's right through here, right? And this would be the hanging wall, okay? And this would be called the foot wall, okay? So the hanging wall has gone down relative to the foot wall, which has gone up, right? Okay, so we call this a normal fault, and which is caused by extension, and therefore if it was related to a plate boundary, it would be divergent. You getting it? This is sometimes hard for students to understand, so I took some extra time to go over it. Okay, so we're going to go through and talk about some structures that go along with each kind of these faults. Here's a strike slip fault. This is the San Andreas, and you can see in this case, you can see it going right across this field and this track. And you'll notice it actually is offset to the right a little bit. This is a right lateral fault. This once again is the San Andreas. Okay, and so it's moved to the right. So if I look at this one, I'm looking on this side, it looks like everything's moved to the right, right? Okay, so that would be a right lateral fault. Now if I was on this side of it there, looking this direction, it would still be right lateral. It just means that it's relative to the perspective of which you're on. Okay. And so this is a right lateral fault. You can see it go right through there, and it even goes across. Actually, I think there's a little bit of splay that goes up that way. A couple cracks there. Okay, and so it moves up in that way across the street. It broke off there too. Here is another fault. This time it goes right through here. Notice the trees have been offset here. Okay, as you go through this orange growth. Now that would be a strike slip fault. Okay. Now in a normal fault, a great example of this would be the basin and range of the western United States. And what's happening here is this area is actually being pulled apart. And as it's being pulled apart, the mountains are going up, the valleys are going down. So the mountains are what we call the footwalls, the valleys are the hanging walls, and you're forming these mountain ranges, these linear mountain ranges that are going back and forth. So my wife grew up in the Salt Lake area, okay, and the mountains to her west were what we call the Ochre Mountains. The mountains to the right to the east were what we call the Wasatch. Now she drove over the Ochre. She would get to the Twila Valley, which then you have the Stansbury Mountains. Then you go off, we call this Skull Valley, and then so forth, all the way down to Death Valley, over where the Sierra Nevadas are, right? So if you look at it in digital elevation model, you can see that here's Salt Lake City right here, okay? Here's those Ochre Mountains, here's the Stansbury Mountains, here's the Front Range Mountains, and it goes all the way across until you get to the Sierra Nevadas here. And each of these linear basins here, these valleys are the hanging walls, the mountains here are the footwalls as you go across, okay? Because it's being extended apart, okay? Forming these, what we call horse engrobens. The horse is the rock that's been thrown up on the normal fault, so usually the footwall, and the graben is what's been thrown down, okay? And that's usually the hanging wall. So in this case right here, you notice here, this is the fault. There's two faults here. There's one there and one on this side. There's even a smaller one right there. And you'll notice the marker bed, this is the hanging wall, which is on this side. Okay, I'll put an H for the hanging wall. And this is the footwall. The hanging wall's gone down relative to the footwall. You can see that on the other side too. The hanging wall's gone down to the footwall. Okay, so these are what we call brittle structures, or what we call horse and graben. The horse is the top, the graben is the bottom. Graben, I think if I remember right, the term for graben comes from grave. It's the low point, right? Okay, it's been thrown down. I think it's French, if I remember right. And horst is like a saddle, so it's almost what with the top of it, it's gone up, or hill. Okay, if I remember right, gone up, whereas graben is the grave. Okay. So now, if we had brittle structures in a place where you have compression, what you're going to do is you're going to have these faults where you have reverse or thrust faults, right? So you're pushing it up on top of each other. Here's the hanging wall. Okay, here's the foot wall, and it's gone up relative to the hanging wall has gone up relative to the foot wall. Very good example is if you had a snow plow. I know we don't get a lot of snow back around here, but if I pushed on it, they'll start stacking up on top of each other, just like what I have here. Okay, where I push it and it will stack up on top of the other one. If I had another one, it might even stack on top of that, and you'll get these big features or big mountain belts. They're very common in places with mountains to form these big thrust faults within the mountain as they stack up on top of each other in a brittle fashion. Okay, so those are all brittle structures. But what about ductile structures? Well, ductile members is very similar. It has same kind of stress regimes, but because it's ductile, it's going to not break, it's going to bend and fold, right? So folds are related to ductile deformation. So here's some examples here where you have different types of folds. You can have very close folds or tight folds or open folds, okay, depending on how far they're apart. So you can have these broad folds like this, where you slowly have a broad fold here, or maybe a really tight fold like that. Okay, so there's different types of folds that you have. You have what we call the actual plane or the hinge. Okay, where's the top of the fold, and then we'll call them different types of folds based off of how they bend. So here's some examples of different folds. Actually, I'm going to stop here, and we'll come back to this in our next segment.